Ever wondered how massive machine like this make a turn so easily with a very minimal effort on the wheel? Hello. Today in this video, we will get to know what make this so easy to turn, and then we will determine which component make it helpful, and then we will determine how to size it. This has been made possible with the help of hydraulic steering unit, which was invented by the Carlson Leon in 1961. But before Carlson Leon invented this hydraulic steering unit, heavy machines were using several mechanical steering systems, which all required substantial physical effort to steer the machine. In early heavy machine for meditating were using tiller wheels for steering. Here you can see the tiller wheel. This one is also tiller wheel, and here it is also tiller wheels. When gasoline engine replaced the steam power in early 19s, steering clutches were added to each track, which disengage the drive power from the inside side of the track. Suppose, let's say you wanted to make the right turn, so steering clutch will disengage the drive power from the right side of the track, and power will transfer to the left side of the track, uh, allowing to assist the tiller wheel to make a right turn. But this approach had some significant drawback, like when going downhill or machine is carrying load, then steering could cause the machine to turn in the opposite direction rather than the intended steering direction. Also, when one track was declutched, all the drive power transferred to the other side of the track, which required to handle the twice the normal power. So later, this design has been improved by adding the track brakes to assist the steering. But this approach also had some significant drawbacks. Differential steering system offered an alternative approach to steering clutch system, where both the track remain powered at the all the time. In steering clutch system, either side of the track have to disengage from the power to assist the steering. But in differential steering system, both the track remain powered at the all the time, but either side of the track have to get brake to assist the steering. So both type of the steering uses mechanical advantage to have the steer heavy machine. But both type of the steering require the substantial physical effort, and it also has a unpredictable steering behavior when it was in under load. So this led to make Charles and Leon hydraulic steering control unit very advantage when it was introduced in 1961. The hydraulic approach isolated the load from the operator, which reduced operator fatigue, and it also reduced steering effort while providing infinite variable control. The basic design principle of the hydraulic steering unit have not changed much, and it is still being used on the many heavy machines. Here it is the exploded view of the hydraulic steering unit, in which the steering wheel is planed to the control spool, and this spool is coupled to the contour sleeve through a centering pin and centering spring. As the contour spool and sleeve assembly turns through the drive shaft, the centering pin makes the drive shaft rotates. This drive shaft is connected to internal georotor, which spin within the georotor assembly. Here is the hydraulic steering unit used on off-highway bogie, which is designed for the off-road adventures such as rock crawling, trail riding, and some other off-road events. Here is the standard hydraulic steering schematic, which uses open center system. Flow from hydraulic pumps enter into steering unit, and based on the steering wheel input, flow enter into steering cylinder. Steering cylinder transfer force to shaft, and due to this vehicle make a turn. Now that as we got basic idea of a steering unit, we will move on to the main intention of this video, which is to find the displacement of steering unit. If you like to know more about the hydraulic steering, you can refer to the these 6 series of the hydraulic steering, for which I have provided the link in the description. Now to find the right displacement for the steering unit, first we have to determine how much weight will be acting on the steering axle. Here you can see the W weight is acting on the steering axle, which is in our case it is 15,000. And then we have to determine the nominal weight of the tire B and kingpin eccentric E. Once determined, then based on value of E upon B, we can determine the coefficient of friction from this graph. Once we got this four value, we can determine how much torque will be required to steer the axle. In For our kit, it is 890. Okay. Once we have got the torque value, then we have to determine how much force will be required to steer the machine. To find out the force, we have to get the cylinder stroke. And to get the cylinder stroke, first we have to find out how much the steering angle will be needed and how much the maximum radius arm. So here it is our uh, maximum radius, and here it is our maximum steer angle. So based on that, we will get the minimum effective radius arm. Here it is minimum stroke length, and at this point cylinder will be at full stroke length. So based on that, we will get required force. Once we have got the required force, we can easily identify the how much cylinder area will be required based on the Pascal formula. So for that, we have to define how much pressure will be required for the system. Usually it is around maximum it is around 250 bar, and pressure rating depends on the machines. For the machine which never be overloaded beyond 80% of this steering circuit really fall, we have to put value at a point 0.8, and for manually loaded vehicle we have to use 0.6, and for the vehicle that can be severely overloaded, then we have to use the value as a 0.3. So based on the Pascal formula, we can get the uh, total cylinder area, and if we have the road diameter, then we can easily identify the how much the bore diameter will be. This is the three bore diameter depending on the three condition. If the machine is using the cross cylinder, then it is this, and if machine is equipped with the balance the steering cylinder, then value it is this, and for machine which are using differential cylinder, then value can be determined as well. So here is the diagram of the wheel loader which is using cross connected cylinder. As you can see that the right chamber is coming on the road end side, and also at the head end side for the right steering cylinder. Here is the snapshot of the Volvo wheel loader which is using the cross connected cylinder. And usually backhoe loader comes with the balanced type steering cylinder, and so for that we can use this value, and for wheel loader we can use this value. Once we have the find out the cylinder area, then we can easily identify the how much the displacement of the steering unit will be required. But before that, we have to identify how much the lock to lock turn will be required, and if the system is using any flow application feature or not. Lock to lock turn refers as the total number of complete revolution of the steering wheel required to move the steering wheel from one extreme position to another extreme position. For example, if steering wheel required 2.5 turn lock to long, then operator needs to rotate the steering wheel 2.5 complete revolution to go from maximum turn left turn to maximum right turn. Usually the acceptable range for most application varies from 3 to 5 turns. Although but it depends on the specific vehicle and its intended use. A lower number of turn lock to lock adding indicates that machine will be quicker and more responsible steering. QM system work by adding a variable orifice that bypass the zero rotor section and deliver flow to directly to the steering cylinder. This orifice remains closed at the low steering wheel speed but gradually open as the steering wheel rotate faster. Here you can see the fast turn implies that the uh, flow some additional flow diverts to steering cylinder directly without passing to the zero rotor system. A typical QM system has a ratio of 1.6 to 1, which means that flow delivered to cylinder is 1.6 times the flow going through the zero rotor system. If the steering unit doesn't have any QM feature, then we can use it as a 1. But it is but if cylinder steering unit has any QM technology, then we have to identify how much ratio is added. So based on this turn lock to lock and QM ratio, we can identify how much the actual steering displacement will be required. So once we get this value, then we can find out near which value it is available at the supplier. So we here we get the 178, but from the supplier catalog, we can easily get it around 180. So based on that, we can identify the actual lock to lock turn will be how much the actual lock to lock turn will be available, and then we can easily identify how much steering circuit flow will be required. Based on that, how much steering wheel input has been given. This wheel input is the same as how much RPM is given to this wheel. So based on this wheel input, we can identify how much the steering circuit will have required flow. So finally, we have got the actual steering displacement and how much circuit flow will be required for our steering system to turn the machine. To access the calculator, you can refer to the link added in the description. And if you get any question or anything to ask, you can directly add into comments, or you can also mail me at info@epichydraulic.com.